So let's begin with the second part. You hear anything? So what this lecture will tell us is, there's a question asked, why do we look at binary objects? So basically what I am going to argue is, the reason we look at binary objects is because that is what is our best chance of directly detecting gravitational wave on the Earth. So I'll slowly work towards that particular theme. What you heard now at the end was that if you knew there was a binary system and this binary system finally merged into each other, what is it that you will see? Later on I will show you the waveform. This was actually the conversion of that waveform into an audio file. So essentially, the system inspirals and finally there is a burst of radiation, which is what you heard in that audio file. So let's begin again like last time with what we know, and what you really know about waves comes from your knowledge of Maxwell's equations. So again the story goes back to 1865, where Maxwell wrote an important paper which is called A Dynamical Theory of the Electromagnetic Field. In this paper he derived for the first time the equation for the electromagnetic wave equation and demonstrated that light is nothing else but an electromagnetic wave. So to remind ourselves, by radiation or waves we mean fields which are not static but fields which transport energy to infinity. So if you have a charge and the charge moves not at constant velocity but if it is accelerated, a part of the field will detach, it travels at the speed of light, and importantly it carries energy, momentum and angular momentum, and that is what we call electromagnetic radiation or electromagnetic wave. Just 20 years after Maxwell predicted it, electromagnetic waves were theoretically experimentally confirmed by Hertz, who produced electromagnetic wave by using an oscillator in one end of the lab and recorded it on a detector which was just 12 meters away. So in the lab you could demonstrate that electromagnetic waves could be created and detected. At that time, when somebody asked him about the importance of his experiment, he is supposed to have said, it's of no use whatsoever. This is just an experiment that proves Maxwell is right. We have these mysterious electromagnetic waves we cannot see with the naked eye, but we know that they are there. When he was asked whether there would be any ramification or impact of his discovery, he basically is supposed to have said, I don't think it will have any impact. But today, if we really ask this question to anybody in this class, obviously the answer is going to be completely different. You don't have to be Hertz. Even if you are not Hertz, you definitely know that our complete life, he is recording me, I am showing you this, you are using your mobile, at home when you watch your TV or do anything, your microwave, or think of whatever you have in your life. If the electromagnetic interaction is turned off, I think most of us will commit suicide. So obviously the important point is that even a very professional and very intelligent physicist finds it very difficult to predict what will be the impact of something fundamental, let's say 100 years from now or 200 years from now. And this moral is what you will see, I will keep on emphasizing in my talk today. So in the morning I have already told you that we have a better theory of gravity than Newtonian gravity, which is the relativistic theory of gravity, and therefore in this particular theory, like general theory of relativity, because it has to be consistent with the principle of relativity, gravity will not travel at infinite speed, it will travel at speeds less than the speed of light, and therefore if the gravitational field of an object changes, these changes will propagate through space, take a finite time to reach objects, to reach other objects, and if you have a time dependent field, these propagating oscillations is what we will call gravitational radiation or gravitational waves. Because gravity is described by the curvature or distortion of space-time, people also say that gravitational waves can be called as ripples in the space-time of general relativity. In the morning I explained to you that there is a uniform part of the gravitational field which can be transformed away, but what is physical is the tidal part of the gravitational field. And therefore you can also say that by gravitational waves we mean oscillating tidal gravitational fields which propagate out from the source. Just as electromagnetic waves are produced by accelerated charges, if you have accelerated masses, they will produce gravitational waves. Exactly like the electromagnetic case, they will carry away energy, angular momentum and linear momentum from the system. Now comes the important difference. Since the gravitational interaction is very, very weak, when gravitational waves travel through space, they are essentially unperturbed. They do not interact with the matter which is on the way, and therefore you can see gravitational waves from very far. You can see gravitational waves from the heart of a supernova. You can see gravitational waves from the beginning of time. And that is the big difference, that gravitational waves will allow you to see things which you otherwise would not be able to see. And therefore, if you are an astronomer, you are very excited because you can see things which you could otherwise not see, so it is a blessing for you. But if it is your job as an experimenter to detect gravitational waves, you will curse it, basically because it is a very, very hard job to detect gravitational waves. Now, once you know that gravitational waves are there, the next thing you have to know is what are the properties of these gravitational waves. So, if you study the equations of general relativity and ask what are the properties of gravitational waves, you find that the properties are very similar to the electromagnetic waves property. They travel at the speed of light, they are not longitudinal but transverse, and they have two states of linear polarization. Remember what is meant by polarization? In the case of electric field, if the charge can oscillate, if the light travels in the z direction, the charges can oscillate in the x direction or the y direction, and that is what you call linear polarization of the gravitational wave, of the electromagnetic wave. Similarly, in the case of gravitation, if you look at how many different independent states of polarization are there, you have to look at the tidal fields which can be created by a gravitational field, and you can show that the tidal fields have the following two configurations. It can either look like this, that means in the plus orientation, or it can look like this, that is tilted by 45 degrees relative to this. And because of that, because of the fact that there are two independent states of tidal fields, you say there are two independent states of polarization for the gravitational wave. Their effect can be measured by taking a ring of particles. On this ring of particles, suppose you act by this particular force, then you will find that this circle will get elongated to an ellipse in this particular direction. It will come back because it is an oscillatory field to this circular orientation, and then in the next phase it will become squeezed in the other direction. So this oscillatory pattern is what you will see if a plus polarization is incident on this beam of on the plane of this particular ring of particles. If a cross polarization is incident, then it will be squeezed exactly like this, but the orientation would be at an angle of 45 degrees relative to this orientation. So that is the reason we say that there are two states of polarization for the gravitational wave, which are called plus and cross. Now comes again the important difference. Now, if you look at the electromagnetic radiation, and those of you who have studied something about radiation, you basically know that in the case of electromagnetism, the leading radiation is given by the Larmor formula, and that formula basically tells you that if there is a time variation of the dipole moment, then there is dipole radiation in the case of electromagnetism. It turns out that in the case of gravity, dipole radiation is not possible because of the fact that to have dipole radiation, you will have to have violation of some conservation laws, and therefore in the case of gravity, the leading order radiation is not dipolar but quadrupolar. And this is the basic difference. Those of you who remember your multipole expansions, you know that as you go to higher and higher multipoles, you get extra factors of C in the denominator. So it means that monopole radiation is stronger than dipole radiation. Dipole radiation will be stronger than quadrupole radiation. So again, not only the gravitational constant is small, but also there are extra factors of C when you look at gravitational radiation. So because of these two factors, the gravitational radiation is much weaker compared to the electromagnetic radiation. Now, if a system emits gravitational radiation, it will lose energy, and therefore the orbit which a particle will undergo will not be the same. For example, even if you have two bodies going around each other in an elliptical orbit, if it didn't emit radiation, it will go on a fixed orbit. But if it emits radiation, that orbit will keep on changing, and you can try to calculate, at what order the correction will come, because it's emitting radiation. One can show, if you analyze general relativity, that the correction comes at a very high order. It comes at the order v by c raised to 5. The periastron precession, which I talked about in the morning, which Einstein discovered, was the cause. The cause of it, he proved, was general relativity. That correction is of order v by c raised to 2. So you can see that compared to the precession effect, this is an even weaker effect. That means if you want to detect whether a system emits gravitational waves, you have to do an experiment which is even more sensitive. You cannot do it by ordinary experiments. So that is the reason that even though Einstein predicted general gravitational waves in 1916, even after 100 years, we don't have an experimental confirmation like Hertz. Remember, I told you that in the electromagnetic case, in almost 20 years, you could verify the existence of electromagnetic radiation in the laboratory, but we cannot do that experiment in the case of gravity. And as I explained to you, the reason is twofold. The gravitational interaction is much weaker compared to electromagnetism, and dipole radiation is not possible in general theory of relativity. Therefore, if you try to convert the mechanical energy of a system into gravitational radiation, unless you have very strong gravitational fields, unless your system is relativistic, you cannot produce gravitational waves. Also, the effect of gravitational wave on any detector will be very, very weak. And therefore, instead of laboratory sources, you really have to look for astrophysical systems where you can create large masses. These large masses can have very large accelerations, and therefore by using astrophysical sources you can produce gravitational waves. And that is the reason that we believe that the most likely sources for gravitational waves for our detectors are situations where there are very strong fields. So that is the reason we talk about neutron star binaries, neutron star black holes. Or if you have a violent event like a supernova or a gamma ray burst, maybe it can be accompanied by gravitational radiation. If you have an isolated neutron star, but on that there is some asymmetry, it can produce again gravitational waves. And as I told you, the most violent event in the universe is the Big Bang, and maybe from the Big Bang also some gravitational radiation can be emitted, which we can try to detect eventually in the future. Not only the experiment is difficult, even the theoretical understanding of gravitational waves took a large number of years. It almost took 50-60 years, because even though Einstein had predicted gravitational waves in 1916, in 1936 he wrote to Bonn. Together with a young collaborator, I arrived at the interesting result that gravitational waves do not exist. Again, you can see that even somebody like Einstein was never sure whether what he was talking or what he was deriving from his equations, whether it was really a physical wave or it was only some coordinate effect. And unfortunately, of course, for us, by the time the paper was published, somebody told him that he was making some mistake in his interpretation, and therefore what happened was, by the time the paper was published, this conclusion which he had originally made, he withdrew it, and therefore in the published paper this erroneous interpretation is not there. And as I told you, the reason it took many years to understand this is basically because general relativity is a very complex theory. You can write it in various coordinates, so you have to be very clear about whether some effect which you are talking about, whether it's a coordinate effect or whether it is a physical effect, whether some singularity which is there in the equation is a physical singularity or whether it is a coordinate singularity. When you try to use exactly the same techniques like in electromagnetism, you try to use retarded potentials, advanced potentials to solve the to solve the wave equations, but it's a nonlinear theory, so you don't know that if you start with one retarded potential and one advanced potential and you add them, whether it will be a solution of the Einstein's equations, etc. So there are a lot of these technical complications, because of which it almost took 100 years, almost about 50 years, for a theoretical understanding of gravitational waves to basically emerge. So now, having said that it's a very difficult experiment, it is also a kind of topic which had a lot of confusion theoretically. Fortunately, as I have been explaining, what really makes the situation much better is the existence of an experiment which tells you once and for all that gravitational waves, whether they are real or whether they are not real. And I will tell you about one experiment which really tells us that there is very good quality data which you can consider as proof that gravitational waves actually should exist, and Einstein's description of it is the right thing. In 1974, Hulse, who was a graduate student of Taylor, basically started looking for observations to look for pulsars. When he was looking for pulsars, he discovered a pulsar which was in a binary system. That means it is a pulsar. That means, as I told you, pulsar is a neutron star which is like a lighthouse, but that lighthouse is not isolated. That lighthouse goes around another neutron star, so it is a binary system. Now, those of you who know about the hydrogen atom, you know that one of the basic problems when you applied classical electromagnetic theory to the hydrogen atom was the following question: if you had the nucleus and if you had the electron, if the electron is going around the nucleus, it is actually accelerated. So because it is accelerated, it should put out radiation, and because it puts out radiation, the atom would not be stable. And the only reason it is stable is because we know that classical physics does not apply. You have to apply the physics of quantum mechanics, and the moment you put in the quantum principle, uncertainty principle, then you can stabilize this particular atom. So here we are in this classical situation where you have two bodies going around each other. Because of the fact that Einstein's theory predicts that they will emit gravitational radiation, you basically can ask whether it will move in a fixed orbit or whether that orbit will inspiral. So this system has been monitored for about 30 years, and if general relativity is the correct theory, gravitational waves would be emitted and the orbit should really inspiral. So what is shown on this particular graph is the thick line, which is Einstein's prediction for a quantity of how the precession, whether the orbit is closed or not, and the points are really the observational points. And you see that Einstein's theory, which predicts gravitational waves, matches exactly with what you observe as the orbit of this particular system. So this particular system shows you that the orbit is slowly decreasing at just the rate predicted by general relativity for the emission of gravitational waves. The orbit is about 8 hours, and in 8 hours it shrinks about 3 millimeters. But because you can make measurements of the orbital period very accurately, you can actually confirm that it is indeed true, and for this discovery these two gentlemen received a Nobel Prize in 1993. Now, I had told you that the precession in the case of Mercury was 43 seconds of arc per century. This is such a relativistic system that in this particular case the precession is 4.2 degree per year. So you can see that it is already a very relativistic system. The V by C for this particular system is 10 raised to minus 3, and yet we can discover the presence of gravitational radiation in this particular system. So the first thing you can be happy with is that gravitational waves are really true. There is an experiment which has already got a Nobel Prize, and therefore the question is that the reality of gravitational waves does not have to be doubted. It also tells us that general relativity is true not only in weak fields but in strong fields, because remember the neutron star has strong gravitational fields. But physicists are not satisfied. We have excellent evidence, but in a sense this evidence is indirect, because we have not made the gravitational wave fall on a detector on the earth and seen a needle move. So we really want to have a direct detection of gravitational waves, and to do that we basically use the most sensitive detectors we can build, and these are these laser interferometric gravitational wave detectors. Why we use laser interferometers I will come to in a moment. The excitement is not because we want to detect gravitational waves. Once we start detecting gravitational waves regularly, we believe that it will be a new observational window into the dark universe, because remember most of the universe is electromagnetically dark. Only 4% of the universe is seen by electromagnetic observation. Once you start opening a new window, it will become a new tool for studying the universe, because it can tell you something about the astrophysics of objects, the cosmology in which we live, and finally from that we can also start studying gravity itself. So it can become an experimental probe for basic physics. So now the challenge is how to build detectors for gravitational waves. So to explain the principle, I told you that if we had a ring of particles and if a gravitational wave falls on this, because it's a time dependent oscillatory field, the ring of particles will be squeezed in a particular configuration, and if you can measure the amount of squeezing, you can say that you can detect gravitational waves. So the next problem you have to do is, if I take an astrophysical source, how much squeezing will happen if I take a ring of particles? Now I will come to that in a moment, but the fact that we are going to have some squeezing means that we have to measure a small displacement, and if you want to measure small displacements, the best instrument as we know today are laser interferometers. So what is shown here is that I have replaced the ring of particles by a laser interferometer, and I adjust the arms of the interferometer so that when there is no gravity wave signal, you put the system in its dark fringe. Now if a gravity wave signal passes through this interferometer, the arm lengths will be changed. In one direction it will elongate, in one direction it will squeeze. So the path length of the light rays changes by a certain amount, and therefore if you have arranged the system in a dark fringe, because of the fact that the path length has changed, there will be some output which will come out of this, or some light or some photocurrent which will come out of this photodiode, and therefore if you can measure this small photocurrent, then basically you can detect the gravity wave signal. So essentially you are converting a displacement into a current, and you try to measure the small current which you will generate. Now the whole question is, how much squeezing will happen? What will be the path change? Whether it will be 1 centimeter, 1 meter, or what? So to do that, we introduce a quantity called gravity wave strain. So if you have two particles which are separated by distance L, if they are squeezed by an amount delta L, take the ratio of delta L by L. By definition this is a strain. So depending on what the strain is, you can say that is the strength of the gravitational wave. So the measure of the effect of gravitational wave is really the strain which it induces. Now let's take a very heavy dumbbell on the earth. Take a car for example, which weighs about a ton, separated by about 2 meters, make it rotate as fast as you can, and you ask how much strain which I will produce. Now obviously I am using some theory to calculate the strain, so I have used the formula which comes from general theory of relativity, which gives you an explicit formula for what the strain is if the mass is known, if the period is known, and so on. It turns out that the strain which you generate with a very massive dumbbell is of the order of 10 raised to minus 39, and you can ask, with the technology which I have today, can I measure such a small strain? The answer is no, you cannot do that. So then what do? You go to an astrophysical dumbbell, which is these two neutron stars going around each other. So if you take a dumbbell made of two neutron stars, where each of these neutron stars is as massive as the sun, suppose it's moving at very rapid speed, suppose it is in the nearest cluster of galaxies, which is the Virgo cluster of galaxies, suppose you ask what is the strain it will produce on the earth, the number is 10 raised to minus 21. And it turns out that with the technology we have today, which I will explain in a moment, this is the kind of strain you can measure. Now how do you measure this particular strain? You have to build an interferometer, not a tabletop interferometer, but an interferometer which is of the order of a kilometer long, because if you take a strain like this and if you take L of the order of a kilometer, the displacement which you need to measure would be of the order of 10 raised to minus 18. Those of you who remember your nuclear physics basically know that 10 raised to minus 15 is like the nuclear dimension, it's a Fermi. So you can see that you really need to measure 1,000th of a Fermi if you want to detect gravitational waves from a neutron star which is going around in the Virgo cluster of galaxies. So this is the basic challenge, and this is the reason why it has taken almost 100 years to get to the point where we think that we can detect gravitational waves. So you cannot use a simple Michelson interferometer, people who do optics really know that even if I build an interferometer which is, let's say, a few kilometers long, this is not sufficient to measure this 10 raised to minus 18 meters. So what you do is create what is called as a Fabry-Perot cavity, so that the light can be bounced many times, about 100 times, so that the optical path changes. So even if the interferometer is only 1 kilometer long, the optical path is 100 kilometers long. And then there is some light which comes out of the photodiode, that to keep this going on for so long, you take this signal which comes out, the voltage which comes out, and do what is called as power recycling. So putting all these techniques together using photodetectors as diodes, it turns out that you can measure the separation not just between two fringes, you can even measure the separation of 10 raised to minus 11th time of a fringe. This is the basic magic, that by using this optical configuration you can split a fringe, and because you are using these photo detectors, you can really measure a very small fraction of that fringe, and this is exactly the trick which we require to detect gravitational waves. So we can say that the interferometer acts like a transducer. It converts the gravitational wave to a photocurrent which is proportional to the strain amplitude. If the strain amplitude is more, there will be more photocurrent. If the strain amplitude is less, there will be less photocurrent. So you can actually convert the strength of the gravitational wave into a photocurrent and make a measurement of it, and that measurement is what will help us detect the gravitational wave. Now I told you that if you want to really measure something which is very small, but if you really look at the interferometer, this interferometer is actually sitting on the earth. It is really being hit by a large number of photons. So even if no gravitational wave is falling on this interferometer, these arms or these test masses or these mirrors are shaking like mad. If you really ask how madly are they shaking, you basically find that they shake for various different reasons depending on the frequency at which you observe them. Suppose you look at the low frequency end. We are sitting on the earth, and the earth is not really stable. The earth has motion because of seismic noise, and that seismic noise is usually is quite high. One can measure it, one knows an estimate of it. So what is shown is that if you go to low frequencies, there is noise because of the earth's motion. At some middle frequencies, because of the fact that there are thermal effects which are there on the interferometer, there is going to be some kind of noise. When you go to high frequencies, because of the fact that photons are not single objects, many photons are falling on the test bodies, you have something called the photon shot noise. So if you really make a measurement of what is the noise because of all these other effects, you find that only when you are in a certain frequency range, which is given, let's say, from 40 hertz to about 1000 hertz, you can measure something which is of the order of 10 raised to minus 18 or 10 raised to minus 19. If you go to low frequencies, the noise is so much that you will not be able to detect these gravitational waves. So the important point is that even if you can build the most sensitive detector on the earth, you cannot go to frequencies below, say, 1 hertz or 10 hertz. Therefore we are in a dilemma, because we have a very sensitive instrument, we have a very nice source which got the Nobel Prize, but we want to see whether the detector which we build will really be able to see this star which got the Nobel Prize. That means this star should really emit radiation at the frequency range in which this detector is sensitive. So this is the question which we have to do. So you ask the question, if you use the general theory of relativity and ask what is the frequency of this Nobel pulsar, the answer comes out to be, you use the formula from general theory of relativity, that the frequency of this gravitational wave is millihertz. It's 10 raised to minus 4 hertz. And as I already explained to you, because of the fact that we cannot measure small displacements at that particular frequency because of seismic noise, we seem to have lost the battle, because though we have a detector, our source is not sensitive at that particular frequency. So do we give up? We don't give up, because we say that, well, I know my physics, and my physics tells me that even though the frequency today is 10 raised to minus 4 hertz, the system is really going inwards and inwards. As it goes inwards, the frequency will slowly start increasing, and there will come a day when the frequency will become in the bandwidth of the detector, and when it comes to the sensitivity bandwidth of the detector, I will be able to see this particular pulsar. Now, how long do you have to wait? Unfortunately, you have to wait for 300 million years. So again, you can see that when you apply the physics which you do, you realize that you are in a situation that from this pulsar which got the Nobel Prize, you will not be around when it comes into the sensitivity bandwidth of your detector. So, do you give up? Then you say, no, I will not give up, because I look at the age, how the number of years it takes for the pulsar to come to the sensitivity bandwidth. It is 300 million years. Now, is this, it is of course much larger than our age, which is 100 years, but is it much larger or smaller compared to the age of the universe? The age of the universe is billion years. So, in the billion years, compared to that, it is much smaller. So, if we don't look for this particular pulsar, but look at the population of pulsars which exists in the universe, even though this binary pulsar is not in the sensitivity bandwidth, there may be some system which may be in this frequency range, and we should be able to see them. So that is basically our basic point. Over the years, many other pulsars have been discovered in binary systems. There is another object which is called the double pulsar, which is even more rapidly moving around. Now this will coalesce in about 86 million years. So our experience basically tells us that our understanding of the population of pulsars basically tells us that not these pulsars which we are seeing, but there should be some pulsars in the universe which would at this particular point be going in their last orbits. So and that is the reason, if you remember, I had told you that we can look at the last 3 minutes of coalescing binary systems, because it's in the last 3 minutes of their existence, their frequency comes in the right bandwidth, and during the last few minutes they put out so much radiation that it outshines the solar luminosity by very large number of factors. So for a small amount of time, the emission in gravitational waves is very high. So the whole point is that we not only have a detector, we also have the nice kind of sources which we are looking for, and therefore this will really answer the question which was asked to me, why do we focus on binary systems? We focus on these coalescing binary systems made of neutron stars and black holes, because it is these systems which at the end of their lifetime come into the sensitivity bandwidth of our detectors. You may ask, why not supernova, which is a very violent event? The point is, supernova, the predictions from gravitational waves from supernova, because the supernova process is such a complicated process, we really can't predict how much gravitational wave will come out of a supernova event. But in the case of a binary system, it is completely governed by the general theory of relativity, so we know everything which you can know about this radiation, and that is the reason we focus on those particular systems. So I have made the case that the late inspiral and merger epochs of compact binaries made up of neutron stars or black holes, they will really provide us strong sources for gravity wave detectors. The detectors are called LIGO and Virgo in the frequency band, as I told you, from 10 hertz to about 10 kilohertz. When they are about to merge, the V by C is much higher. It's almost of the order of 1. It is much larger than 10 raised to minus 3, which we saw for the Nobel pulsar. And therefore we can say that we have guaranteed sources for the gravity wave detectors. We really don't know how many should be there. So if there are enough of them, then we should be able to see these gravitational waves. From our elementary understanding of the fact that they are going very fast, they are going into strong gravitational fields, we can predict their amplitude should increase with time, and their frequency also should increase with time. But as I explained to you, even though we have very strong signals, when you compare to the noise of the detector, though you can say that we are in a situation where we have weak signals buried in the noise of the detector, and therefore straightforwardly if you look at the output of the detector, you will not be able to see this particular signal. You have to use engineering techniques which are called match filtering. Only then you will be able to detect this gravitational wave and characterize these gravitational waves. And that is the reason why over the years you really had to use the general theory of relativity and predict what is the waveform which will come out from these coalescing binary systems. And over the years the group in which which I had in RRI basically worked on this particular problem in collaboration with our colleagues in France. There has been a lot of progress in this two body problem in general theory of relativity, and by our efforts we today know all that is required to really make a detection. So it's a very interesting situation where we really have to do a very accurate theoretical calculation, because only then the experiment will really succeed. What I will now show now is a couple of projects which students and my colleague Ajit, who was actually from MGU earlier, basically did. So basically this particular simulation tells you the richness which you will see in the waveform once. So what is shown here are two stars which have a spin, and that spin is really aligned, and as they inspiral inwards, you basically see that the associated waveform can be calculated by formulas which come from general theory of relativity, and then you will find that the waveform has a lot of structure which is there. So you can see the last ping which you hear is basically the ping when they sort of merge and become one neutron star, or sometimes depending on the mass it becomes a black hole also. Now if the spin are not aligned, but if they are arbitrarily oriented, you can see that the waveform modulations are much richer. So depending on the time scales which are there associated with this particular problem, you will get these various modulations, and you can almost predict, starting from very early times, eventually when these two stars merge, what happens. So this is a very nice simulation which was done by students, visiting students in Ajit's group. And what I wanted you to see is that you see that there is this structure in this particular waveform. So if you really look at this particular waveform, you will finally work back and say something about what the system was. What would be the mass of this particular system? What was the spin of this particular system? Whether the spin was it will be aligned, not aligned, etc., etc. And that is what is meant by saying we will be able to do gravitational wave astronomy. Once we start making observations of gravitational waves, we will be able to reconstruct the waveform of those systems, and from that waveform we should be able to say something about. So this is a simple slide to explain what is the notion of match filtering. So as I told you, in the case of a binary system, the waveform should really be a chirp. Its amplitude increases, the frequency also, as you can see, increases. Will the output of the detector reflect this particular waveform? The answer is no. The output of the detector essentially looks like this. And why does it, why don't you see this in this particular waveform? So just look at the scale. Compared to this, which is of the order of 10 raised to minus 16, this is about 1000 times weaker. So even if in this noisy data this signal is buried, just by looking at this you will not know whether a gravity wave signal is buried in your data. But if you try to make a correlation between this noisy data and this signal, then you will find that in the correlation you can sort of pick it up. When you run this correlation, you basically take this waveform and slide it across this noisy data, calculate what is mathematically called the correlation of this waveform with that particular waveform, you can very easily see that even though it is 1000 times weaker, it is a signal like that is there. If you change the parameter of this particular waveform, you will not be able to locate it. So not only you know there is a signal like this, you also know what are the parameters of this particular signal, and that is what is called as match filtering. So all the people who work on data analysis of gravitational waves essentially have to work within this particular framework. There is a group of people who produce these waveforms. There are a group of people who try to find out techniques by which in the noisy data you try to find out what kind of signals are sort of buried and what is the significance of this particular thing. So this is a real complicated exercise which involves many different disciplines, and that is what really makes the whole exercise very exciting. What is the status of these particular detectors? The status of the detectors is amazing, and as I said, there is this set of people, some of them whose pictures I have given you here, I call them extraordinary gentlemen. For example, the first person who basically said that laser interferometers can be used to detect gravitational waves were these two Russians who basically tried to talk about it. Then there were students like Forward, groups in Germany which built the first prototype detectors, people like Mears who brought about techniques which we use for improving the sensitivity of the interferometers. This is Joe Weber who started the whole field. He built not a laser interferometer but something called a bar detector. And then the father of this particular discipline, which is Ray Weiss. I normally like to put two pictures of him. This is how Ray Weiss looked when he started the whole exercise when he was a young faculty at MIT, and this is how he is today, 80 years old but very active in this particular subject. This is Ron Drever who led the effort in Caltech. He is in MIT incidentally. This is Kip Thorne who actually started the activity in Caltech. Again, I have two pictures of Kip. Kip when he was a young faculty in Caltech when he joined. Kip as he is today, and those of you who have seen Interstellar know that he was the script consultant for the Interstellar movie, the science consultant for that script. And these are the people who built the detector in Virgo. So because of the hard effort over almost 40-50 years by these set of people, the students who worked with them, the postdocs, we worked with them, we built the interferometer which is called LIGO, which is 4 kilometers long in US at a place called Hanford. And because of the fact that it is a very tough experiment, you want to be sure that your system is really detecting a gravity wave signal and not the noise from some car. You put another detector as far away from that as possible at a place called Livingston, and therefore if you really see a signal here and here with some consistent parameters, only then you will believe that you have seen a gravitational wave. For the rest of my story, it is very important to mention that originally the Americans had planned to put one interferometer here, but in the same beam tube originally their plan was to put two laser interferometers. This is the detector which is 3 kilometers long, the European detector at a place called Cassina. This is the Virgo detector, and over the years these detectors achieved. So what is plotted here is the design sensitivity for which they wanted to build this instrument, and what is shown is that gradually by understanding the instrument better and better, finally they achieved the sensitivity which they wanted to achieve, which was basically of the order of 10 raised to minus 19 meter. This is what they wanted to achieve. Now the question which you will ask is, with this sensitivity, did they really detect gravitational waves? The answer is no, they did not detect gravitational waves, but we are not surprised for the following reason. If you ask, based on our understanding on astrophysics, how many events should we be seeing? It turns out that you can see one neutron star coalescence per galaxy per 10,000 years. That means in 10,000 years, one event will happen in one galaxy. And the number of galaxies you could see with initial LIGO was only about 100 galaxies. So in the 1 year where you took the readings, you did not really expect to see any event in the initial detectors, even though they had become very sensitive. In spite of that, a lot of astrophysics could be done by using these observations, and if you look up the net, you will find many papers which talk about astrophysics which come from these null observations. But then, at this same period, did anything happen in India? Yes, as I already told you, there were two different activities which happened in India. One was an activity at the Raman Institute on source modeling, and another activity at IUCA under my distinguished colleague Sanjeev Dhurandhar, who basically worked on very many different techniques for doing gravitational wave data analysis. And we tried to get an experiment also done during that particular period, but unfortunately that was not funded. Fortunately, all the students who worked in this particular groups at IUCA and RRI, they went to different groups abroad, and today I am very happy to say that all of them are back in India and they are at faculty positions, and our gravity wave effort today is led by this younger generation, not by the older people like me and Sanjeev, who essentially are on our way out. So the whole point is that in the coming decade, we want to improve these detectors. The detectors which had achieved this sensitivity, we want to improve it by a factor of 10. And this is exactly what is called as the advanced detectors. So the advanced detectors will achieve higher sensitivity by a factor of 10. And if your sensitivity goes up by a factor of 10, you can see 10 times further, which means you can see 1000 times the volume, and therefore if you have a homogeneous universe, you can approximately say that you will see 1000 times the event rate. So we are in this era of advanced gravity wave detectors starting 2015, and this experiment already is on board. It's a very complex, very nice kind of experiment. So if you really go and see it, there are so many complicated things, but at the end of the day, everything has to mesh together and work very well. And if you really ask, how many events do you really hope to see by using advanced LIGO? Our knowledge of astrophysics basically says that at 90% confidence level, maybe we should be able to see 40 neutron star mergers, 10 neutron star black hole mergers, and about 20 black hole mergers. Uncertainty in astrophysics can make this as small as 0.4, can make it as large as 400, and similarly the numbers are given here. So as you can see, we are neither choosing the very optimistic number nor the very pessimistic number. We are choosing what is called in statistics as numbers which are numbers at 90% confidence level. So we think that this is what we will really be seeing in the coming years. So we were not surprised that we didn't see anything with initial LIGO. So it would really be surprising if we did not detect anything with advanced LIGO. And this is the important point I want to tell you. We are in this epoch of detections basically because if you use those same rates, advanced LIGO can see 100,000 galaxies. So in principle, you could even see one event per month. So advanced LIGO is expected to be a discovery machine. It is exactly like the LHC, when it was turned on, and we expected that in the next year or two, you would see the Higgs boson. So we are exactly in that particular phase where we have turned on our advanced LIGO. It has a certain amount of sensitivity, and with that sensitivity, which gradually will be improved over the next 3 or 4 years, we expect to make our first direct discovery of gravitational waves. So let me just then say that once you start having detection, what should you do afterwards? Now there is a committee, international committee, which is called the Gravitational Wave International Committee, which in 2010 laid out the plan for what we should do with gravitational waves over a 30-year time scale. And their basic point was that once detections become routine, you should really try to locate sources on the sky. And to locate sources in the sky, as I will explain later, you cannot work with only detectors in Europe and America. You really have to build an international network. And that was really the motivation for us to set up this IndIGO Consortium in 2009, where we basically said that if you really want to get into this particular field, you should not only have source modeling and data analysis, you should also get into the experiment, and that was the start of the IndIGO Consortium, which eventually led to the project which I am going to talk about in my next few slides, the project called LIGO-India, which will facilitate internationally the launch of gravity wave astronomy. Now let's ask this particular question. If you have an optical detector, optical telescope, you can point it and say that, well, the radiation is coming from this particular star. Is a gravity wave detector a gravity wave telescope? The answer is no. Basically because of the fact that even if I have the earth and if I have a detector here, even if gravitational wave comes from below, it will excite, because the earth cannot stop the gravitational wave. The interaction of the gravitational wave with the earth is so weak that, which means that if gravitational wave comes from any part of the sky, except for some trigonometric dependencies, my detector will always be affected, which means I don't know from where my gravitational wave is coming. Even if LIGO detects a gravitational wave, where it is on the sky, I would not be able to say. But then how do you say where is the radiation coming from? Because unless you know where it is coming from, you cannot say something about the source. Now you ask the question, how do police try to identify where a cell call is coming from? The way you do it is by triangulation, right? If you want to know from which cell phone the call is coming, you look at 3 different towers, and from each of these towers you try to locate where the thing is coming. Once you use one tower, it should be on a sphere. Depending on the time of arrival of the signal, you know it will be on a sphere. If you take one more, it will be an intersection of these two things, so it will be on a circle. If you take one more, you will be able to break the degeneracy, and that's exactly what you do here. That if you have 2 detectors, the thing should lie on a ring. If you have more detectors, there are more rings, and by looking at the intersection of these rings, you would be able to know where the radiation is coming from. And that is exactly why you cannot use one detector. You really have to use a network of detectors. Now it turns out that if you have these detectors in Europe and US, these detectors are very close by to each other, and therefore if you try to do a simulation of how well the sources in the sky can be localized by using the existing network of detectors, you find something interesting. You find that if you had 2 detectors in Hanford, one detector in Livingston, one the Virgo detector, these sources are well localized, but sources in this part of the sky are not well localized. The error bars are very, very large. Just take that one of those detectors which are there and move it to India, and immediately you find that over most of the sky you can localize the objects very, very well. This is why the international community was very much interested in not putting the detector in the same beam tube, but move it as far away from US and Europe as possible, and the project therefore was called the LIGO-India Project. So the LIGO-India Project really is a collaboration project between the US and the Indian group. The detector essentially is already available with them, but a lot of things have to be done about finding a site, building a vacuum system, setting up the optics, etc., etc. That has to be done by the Indian group, and that is a project which will take about 10 years to build, 5 more years to take readings, etc. And this project, if you want to look at the details of it, you can look it up in the net. If you go to the IndIGO website, you will find the full proposal available on the website. So by 2022, if we get our funding, we will have these detectors in US, Europe. There is a Japanese detector currently being built underground, and the Indian detector which is supposed to come online by 2022. When will the advanced detectors see something? As I already told you, 2015 these readings have already started, and therefore in the first set of readings itself detections are possible, because we have a very sensitive instrument which can see much further than the initial instrument. But as I said, we have to be very lucky to see the detections immediately, but in a few years time we definitely must see these detections, otherwise our understanding of astrophysics is completely wrong. So we believe that detections are possible in the near future, but they are likely over the next 2 or 3 years. And then, as I explained to you, once you have detections which are becoming routine, what we would like to do is locate those sources in the sky. If you want to do follow-up observations by electromagnetic telescopes, you should localize them in a region which is smaller than 5 square degrees, and then you will see that only when LIGO India joins the network, you have a significant number of events by which you can localize them within 5 degrees. Till that time the number is sort of rather very small. So that is the reason we believe that once LIGO India comes online and joins the network, we will be in the epoch when gravity wave astronomy will really start seriously. Once gravity wave astronomy really starts, what kind of things will you be able to do which you cannot do today? For example, suppose you observe gravitational wave which is coincident with gamma ray bursts. It will tell us that short gamma ray bursts are really happening because a neutron star is coalescing. If you can find gravity wave signal from a supernova, it will say something about what is happening in the core of a supernova. What is the engine which is driving the supernova? When you start doing joint observations in gravitational waves and electromagnetism, we will be able to have independent measures of distance and redshift. Therefore, precision tests of cosmology become possible, and over the last couple of years, the LIGO project has had MOUs with many, about 70 astronomy groups, high energy physics, high energy astronomy groups, the radio groups, etc., etc. And therefore, what we really plan to do is that once we detect a gravitational wave, we will send them an alert, and then they will point their telescope to that particular position and try to see whether they see an electromagnetic follow-up. By doing these particular observations, eventually we think that we will be able to say a lot about what is the equation of state of neutron stars, whether the nature of black holes in general relativity is exactly as general relativity predicts. Is the gravity the correct theory of, if general relativity the correct theory of gravity? So many other things will be eventually answered in the next 10 or 20 years once routine observations start happening. So therefore, we are in this situation where we already have, as I explained to you in the morning, many windows by which we look at the universe, but most of them are electromagnetic, and therefore you can only see about 4% of the universe by using this particular window. If you add a gravity wave window to this, what you can say about the universe is going to be remarkable. The gravity wave spectrum also extends over a large frequency range. Today I talked to you only about the ground based detectors, but already people are talking about the possibility of a space detector. Only by using space detectors can you go to frequencies which are of the order of millihertz. So that is what is shown here. Then there are observations of pulsar timing, which again can detect gravitational waves from supermassive black hole binaries, etc. And if you want to look at gravitational waves from the Big Bang, you have to build more specialized instruments. People have been talking about it for many years, called inflation probe. So you can see just as you have a big frequency range in which you do electromagnetic observations, there is almost 2 decades of frequency in which gravitational wave astronomy can be done, and this is what excites us. This is something which will happen over the next 20 to 40 years. Even though I am a theoretician who spent all his life doing gravity wave theory modeling, what excites me about this project is not the theoretical calculation or the fact that gravitational waves will be detected. I am really excited by the fact that this experiment involves technology which are at the forefront of research, and there are many technologies which are basically involved. So for example, what is shown here is the LIGO-India Project, which is spearheaded by the IndIGO Consortium. It began with fundamental physics coming from general relativity. As I said, it can say something about precision experiments. You can look for signatures of quantum gravity in gravity wave observations. So we really came from here. But the experiment will only succeed if all these technologies which are involved, which are sophisticated, they will happen. And as you can see that if you succeed in these experiments, in this particular experiment, these technologies will improve. So anything in India, any experiment in India which will use this technology will also become more sophisticated. can also see the interface with astronomy, multi-messenger astronomy. We have recently launched an astrosat satellite, so we can try to do joint observations between gravitational waves and the X-ray band. There can be radio observations with GMRT, etc., etc. So you can see that there is a lot of overlap with many other communities in India, and that is what is exciting to me. So basically, I started with one particular story about the electromagnetism. Let me end with another story which is related to the neutrino. Neutrinos were discovered in 1930 when people were doing beta decay experiments, because when you looked at the end state of the beta decay, you had to say that there was a third particle in the interaction, and that third particle was postulated as neutrino by Pauli. Nobody had seen a neutrino at that particular time. And if you wanted to be consistent with experiments, the neutrino mass had to be assumed to be massless. So you can say that the indirect evidence for the existence of neutrino is very strong. Nobody had seen a neutrino at that particular time, and it was only in 1953 in a reactor experiment people called Cohen and Raines really made the first direct detection of a neutrino. Something strange happened after that in 1969. The sun, we know, produces its energy by nuclear reactions, and therefore there must be neutrinos coming out of the sun. So you can predict how many neutrinos should come out of the sun, and do we really see so many of them when you do an experiment on the earth? It turned out that you were not, based on your understanding of the solar model and about nuclear physics, the number of neutrinos you saw on the earth was much smaller than what you predicted. This was basically called a solar neutrino puzzle. This remained a puzzle for many years, even though neutrino physics got a Nobel Prize for many different things which happened. But then in 1998 and 2001, people observed what are called as neutrino oscillations. That means even though you begin with one kind of neutrino at one particular point, after some time that neutrino changes and becomes some other type of neutrino. So if you were only looking for this type of neutrino on the earth, you would find less number because they have got converted to something else. So this neutrino oscillation really was demonstrated by these two people in Canada and in Japan. And because of the understanding of this neutrino oscillations, immediately one can say that neutrino oscillations cannot happen if you do the theory and understand it. That is, the neutrino is massless, so neutrino oscillations will not happen. So therefore, the moment you try to understand this astrophysical problem, it told you that our assumption which we started out with had to be modified after some 70 years. Neutrino is not massless, but neutrino has a small mass, and this is exactly why in 2015 these two gentlemen who were responsible for these discoveries got the Nobel Prize. So this basically tells us that in the case of gravity we are exactly in that kind of situation. We have the binary pulsar observations. It is exactly like the beta decay phase, because by indirect observations we know gravitational waves must exist. We are building gravity wave detectors, we have built gravity wave detectors, we are attempting direct detection of gravitational waves. This is exactly like doing the experiment which Cohen and Raines did. And then over the next few years or over the next 20 years, we will make many gravity wave observations and see whether, like the solar neutrino, some puzzle or discrepancy arises. If it happens, then the subject of gravity wave astronomy will lead to new astrophysics, or it will lead to physics beyond the general theory of relativity. So we are in a win-win situation, because if the gravity wave observations agree with general theory of relativity, it is good for us. If it is bad, it is even better, because if the agreement is good, we know Einstein is 100% right, but if it is bad, we know that Einstein is not completely right. There have to be other aspects of gravity and so on. So we will find the corrections to Einstein's theory of gravity. So I hope I have sort of convinced you that the starting up of this particular detector is really going to open a new epoch in our understanding of the universe. As was mentioned in the introduction in the morning, last year was the year of light. It was also the centenary of the general theory of relativity, and we were hoping that in that eventful year our government approval for LIGO-India will happen. Unfortunately, it has still not happened. We are still waiting to hear from the cabinet whether the project will be funded or not. But it's an exciting time. We hope the government understands the importance of this particular experiment. So my last remarks, astronomy really began 4 centuries back when Galileo began with his telescope and started pointing it into the heavens. Einstein gave us the general theory of relativity about 100 years back, and I hope I have convinced you that a major revolution in astronomy is just around the corner, and the LIGO-India project will play a key role because it is an important element in the global network. I have also told you that there are many things in the universe which you cannot see by using electromagnetic radiation, and you can only reconstruct it by the gravitational interaction, because everything has gravitational interaction. So if you find gravitational waves from these things which you have not seen before, that is really going to be adding to our knowledge of the universe, and as I explained to you, LIGO-India will play a key role in understanding the universe. Again, as I said, Einstein today after 100 years seems to be right, but we don't want to take it for granted. We want to make sure that he's 100% right, because many things about gravity we don't understand, especially the quantum aspect of gravitation. So we really have to eventually understand gravitation over the next many years, and therefore we expect that from the observations we will do with gravitational waves coming from various astrophysical objects, we may get some clue about what is really the correct theory of gravity. With that, let me stop my presentation.